Okay, welcome back. And we're going to be starting 12.5 today. Which is triple integrals. So the premise is going to pretty much almost stay the same, right? When we're doing this integration, it's like this partial integration where everything else is kept a constant. So let's kind of dive in and see when we would like to use a triple integral. So let's now consider triple integrals over a rectangular region. So we'll call this region R. And it's the set of all points x, y, and z such that A is the lower bound for x, and then we have an upper bound of b. Then we have that y is bounded between c and d. And then we have z bounded between some constants, maybe r and s. So just like how we did rectangles, we're looking at these boxes now. So we're going to subdivide into these boxes. We can create sub boxes. Maybe we call these B of I, J, K. And they go from xi minus 1 to xi. They go from yj minus 1 to yj. And then z k minus 1 to z k. Each with volume that will denote this delta v of ijk. And it's the length, width, and the height that we give this box. Okay, so each sub box has a sample point. Xijk star, Yijk star, and Zijk star. The Riemann sum is then I equals 1 to some L, j equals 1 to some M, and then we have k equals 1 to some n. So this is the number of subdivisions in each direction. And then we have f at our sample point times the volume of each of those boxes. So like we've seen before, in the limit, that we have that each length, width, and height of these boxes goes to 0, we arrive at the triple integral. So this is over our region R of f, x, y, and z, dv. If the limit exists. Okay. So let's look at a theorem, and you've actually kind of seen this before. It's again Fubini's. So actually Fubini's theorem is a lot more complex than we're making it out to be, but for our cases, this is what it implies. If f is continuous on some domain we'll call B, the rectangular box, then our triple integral on the region B of f of x, y, and z dv is equal to our triple integral with our bounds on x, our bounds on y, and our bounds on z that make up this rectangular box. So now we can also keep going with this and say, just like how Fubini said, if we had constants when we're over the box, right? So it's really important because I've seen this so many different times where students think they'll write down these bounds and they don't think it means a rectangle, right? The only time you have a rectangle or a box is when these are all constants, right? So if you don't have a box and you have constants as all your bounds, something's up. So if we are in a box The ordering of dx, dy, dz doesn't matter because it could be a type 1, a type 2, or maybe even what you kind of call a type 3, right? In this three-dimensional space now, right? So all of the orientations, and I'm not going to write them all out because there's a lot, but you could always interchange these because of the fact that it's on this rectangle. You can always do traces in one direction and then traces in another direction and so on. Okay, so let's talk about triple integral over a general region or a general bounded region. So before we kind of dive into this, what is the triple integral doing? So before, maybe we had some rectangular domain, and if we went dy dx, what happened was we added up all of the traces in this y direction. So we have all these traces in the y direction, and then we follow that up by adding up all of the traces. Or we could do vice versa. We could add up we could have a bunch of horizontal traces and then add up all of those. So what does it mean when we have 3, right? So you can think of it as maybe this has an extra dimension that is pointed out of the screen. And if we do the same orientation, maybe we do vertical traces. We add up all of those traces on the first level. Now I move up maybe out of the screen a little bit. I make a bunch of traces and I add them all up. And then I go to the third level and I keep doing that over and over and over again. So you have these traces and then you have areas that you create. And then you stack all of those areas together and then you add up all of those areas. So it's like, you keep doing the same type of behavior. So you create this surface by doing this, but to create a volume, you continue in and out of the screen here. So let's consider the region. We'll call this one E. And it is all of the points X, Y, and Z such that all of the ordered pairs that are made up by X and Y exist in some other domain that we'll call D. And then we have functions of 2 variables that bound the Z component. We say that D here is the projection or shadow of E onto the XY plane. So we can write at the triple integral over E of the function f of x, y, and z dv is equal to the double integral over the region D And then the single integral bounded by u1 and u2 of f, x, y, and z, dz, dA. So I can't stress enough how important it is to understand what this D represents. Imagine that you have a sphere that's floating in R3. The projection, or the shadow that's cast, so if you take all of the elements and you kind of just project it down onto the XY plane, you get a circle, right? So that's what D looks like. It's not what's touching the XY plane, it's the entire shadow that this thing casts. So we have some standard integral. Now we have bounds that have x and y functions. And then once we perform this is just a normal double integral that we've been used to. So we look at our domain and we figure out, oh, maybe this is a circle, maybe I convert it to polar coordinates. I never said anything about this being Cartesian. So we could do this guy here and then do the area integral as we see fit. So just for an example, perhaps D is a type 1 region. E can then be written as the set of all points in R3. So we have x, y, z, where A and B bound x. Then maybe we have a function that bounds y. It's a function of x. But then we have the original bounds for z, which is a function of both x and y. So it was kind of arbitrary for us to say that we were projecting our object to the xy plane, and z is bounded by functions of x and y. It could have been a combination of this. So we could have just messed around with this a little bit. Perhaps another way to write so maybe instead E is the set of all points such that maybe y is bounded by D. I have that z is bounded by functions of y. And then I have that x is bounded by functions of y and z. And there's not like a tell-all. You can't just say, oh, I know this is how I need to be doing this problem, right? You could probably do it a number of different ways, and maybe some are harder than other ones, but the only way is to get practice with it. There's no like table that you can look up. So if you look at these type of objects, how do I kind of break these things up? Do I even want to do Cartesian coordinates for the area part, or do I want to do polar coordinates and you got to mess around with it. You have to get some practice, but we're going to do some examples to kind of get familiar here. So I'm going to say it again. The first thing we need to do is plot. I think the first thing you should plot is the solid region, if you can. Just get an idea of what this thing looks like. The second thing would be the projection. So once you decide where you're projecting your object, so if you have some volume and you decide, okay, I'm going to project this to the YZ plane. What does it look like on the YZ plane? What does that shadow look like? Maybe you decided that you wanted to project to the XZ plane. What does that shadow look like? Maybe do all of them just to see if any of them stand out to you as a better region to perform a double integral over. And it also kind of gives you an idea of what the solid region looks like. Okay. So for our first example, we're going to evaluate the triple integral over E z dv when the region E is the solid bounded by x equals 0, y equals 0, z equals 0, and the plane x plus y plus z is equal to 1. So this creates a closed region. First thing I'm going to do is I'm going to try to plot this guy. So I'm going to make my x, y, and z coordinates here. So we can easily figure out when this plane hits the like xy plane, the yz plane, the zx plane to figure out when it intercepts maybe these axes. So it turns out that there are 4 points that we can, or sorry, 3 points that we can easily figure out here where it hits each of these. So if y and z are both 0, then x is 1. So I can say this is 1, 0, 0. So it hits right there. And again, if I maybe plug in 0 for 2 of these and keep the other one to solve for, it's always going to be 1. So if this is y, z, and x, here I have 0, 1, 0. And then here is 0, 0, 1. And that's enough for me to kind of sketch out this plane. I know that if I at least connect these dots, this will create the plane. So we're looking at this. And then the back of this is all bounded, right? So the YZ plane, this guy right here, is the bound. We also have the XZ plane. And then we also have the XY plane from these x equals 0, y equals 0, z equals 0. So this is the volume that we're observing here. And we're trying to integrate over this volume z dv. Okay. So this is actually a really nice shape because it's very convenient for us to project in a number of different directions, right? And I don't want you to kind of take this for granted, but imagine if you look down at this object. So we're going down this way, we're looking down, right? the thing that it looks like, the shadow that it casts is going to be the largest or the furthest reaching point in any direction when we're looking down. In fact, because this triangle starts really narrow, and because the origin is also included in it, right here, right? So I know that my projection at least includes this here. I also know that it includes this line. If I think about this hypotenuse looking thing projected down, this projected down as well. And the object that it looks like on the XY plane is in fact what is touching the XY plane. That's not always the case, but for this object, it's pretty clear that if I look down at this, it is the triangle that we're kind of describing here in the XY plane. So if we're projecting to the XY plane, that means that we're integrating Z first, right? We're always integrating the thing that we're projecting into the direction of. So if we decide to integrate over Z first, and because this is a nice shape, we could have done actually, we could have projected to the YZ plane or the XZ plane, but we're going to just choose arbitrarily. We're going to do the Z one first. So we're projecting to the XY plane. It goes from Z equals 1, or sorry, Z equals 0 to Z equals 1 minus X minus Y. So how did I get that? So remember, our plane is the equation X plus Y plus Z equals 1. And same thing, we're just going to draw arrows to kind of figure out what's happening here. I start at Z equals 0, and then I come up and I hit this plane. So maybe it has different heights. You know, it's a lot shorter near this bound here, but it always comes up and then touches this plane. So Z goes from 0 to the plane equation, solve for Z. The projection of the, I should say onto, X onto the XY plane is then, so we're doing our second sketch here. What does the region at the shadow that's cast? Well, we knew in the XY plane, it was going to end up looking like a triangle. We also know that this point here is 1, and this point here is 1. This is the furthest reaching of the function in this particular direction, so it casts this triangle as a shadow. This is our region D. And in fact, we can solve for this line pretty easily. This is Y equals 1 minus X. So then we can choose to do Y next. And of course, we could also do X next as well. We're just going to arbitrarily choose Y here. This is both a type 1 and a type 2. Now Y goes from 0 to y is equal to 1 minus x, right? We can draw some arrows here. Y goes from 0 out to this function, 1 minus x. And then x goes from x equals 0 to x equals 1. So the triple integral is then our three sets of integrals here. Our integrand is z. We went dz, then we went dy, and then we went dx. We said that z went from 0 to 1 minus x minus y, and then our projection, the shadow, went from the y coordinate went from 0 to 1 minus x, and then finally x went from 0 to 1. And this is the setup to do this volume integral here. So let's go ahead and actually do out these integrals. So we can integrate with respect to z first. So we get a z squared over 2, z equals 0, and z equals 1 minus x minus y, dy dx, integral from 0 to 1, integral from 0 to 1 minus x. This becomes 1 minus x minus y squared with a 1/2 out in front, dy dx. So we can actually FOIL this out. The 1/2 can be pulled outside. It's just some constant. So pull out the 1/2, 0 to 1, and then 0 to 1 minus x. So I could FOIL this all the way out, but what I'm going to do is, because I know that I'm integrating with respect to y, I'm going to pretend like this is one term and this is the other term when I'm doing my FOILing. That's perfectly fine. So then I'll have 1 minus x squared minus 2 times y times 1 minus x plus y squared dy dx. And like I said, you can still FOIL these out further. You just have more terms. There's more to keep track of. Okay, so now we can do our y integration. So we have 1/2, the integral from 0 to 1. We perform a y integration, so we get 1 minus x squared times y minus y squared 1 minus x plus y cubed over 3. Y equals 0, and y is 1 minus x. And then I have a dx. Okay, so we plug that in. Okay, so there's a y term on all of these. So if we plug in y equals 0, it doesn't contribute. So we can think about plugging in this 1 minus x. Well, this becomes a 1 minus x cubed, right? Minus a 1 minus x cubed. So these terms end up canceling. And then I have a 1 minus x cubed over 3. So I can bring that third out, and I can have 1/6 times the integral from 0 to 1 of 1 minus x cubed dx. You could FOIL this out. You could do a u substitution, however you want. This ends up being 1/6, and then negative 1 minus x to the 4th over 4, x equals 0, and x equals 1. We can go ahead and plug that in. So notice when we plug in the x equals 1 term, we get 0 here. But our actual contribution is from the x equals 0 term. This becomes a 1 over 24. Okay. That was our first triple integral. Wasn't too bad, right? And it was only of just z. Things could be worse, and the bounds actually weren't that bad. But now you can see why it was so important for us to figure out how to do these area integrals, because our triple integrals certainly are going to rely on that. So now we have to cast this projection, and then we do this area integral, this double integral. Shouldn't it be negative? No. I don't believe it should be. You're subtracting a negative there. We could also think about it logically, right? If all of the values, the things we're integrating over are z, right? So maybe this is a good point. Always question these answers, right? So should it be negative? We look at, we're integrating this thing, z, over the region where z is always positive. So we're adding up just a bunch of positive numbers, right? So I certainly should imagine that this guy ends up being a positive. Did you forget that we were subtracting and there's a negative here? Does the triple integral represent volume as well? Do not, sorry, this is gonna come out harsh, but it's not. Don't think about these integrals representing, a triple integral doesn't always necessarily represent a volume, but people typically say a triple integral is a volume integral because it's over a volume, but it might not represent volume itself. Its outcome might not produce volume. What if you have an integrand of 1, it will calculate a volume of the region that it's over. Similar to if you have an integrand of 1 and you do an area integral or a double integral, you get the area of the region. This, if you have an integrand of 1, will generate the volume of the region that's discussed. But imagine we had an integrand that wasn't necessarily 1, right? What does this represent? And we're going to talk about applications for triple integrals. But certainly you could calculate a volume with a triple integral, right? But always start to think about this is just a sum. We don't know that it's actually calculating something. We're just using it as a tool. Okay, so with that, so that was a very good question, by the way. So with that, why don't we take our 5-minute break? And I see that Heather is on, and then we can get started with recitations.